and welcome back. Now let's look at some of the laws of Boolean algebra. What are some of the rules we'll use? What are some of the principles, properties, identities we're going to use for Boolean algebra? I love this. Let's go one by one to take it really slow to make sure you understand how each one works. So there's a kind of a parallel set of laws that are actually interesting in this way. So there's there's a beautiful duality that kind of comes to the front when we're talking about Boolean algebra. The duality is parallel universes, yin-yang, good versus evil, dark side and the light side of the force. You have here 0 and 1, and an or. Okay, so a lot of times you're seeing even these rules have kind of one side versus the other side of that. So let's take a look. The first is the law of complementarity. This says x and its complement. What is the property when you multiply them or when you add them? Can you ever have a case where you can be both true and false? I can be both x and not x at the same time? Never happens. So that's 0. Contrast that with what happens if I'll be happy if I have, a burrito for dinner, or if I don't have a burrito. Well, guess what? You're always going to be happy, because one of those is going to be true. If either one is going to be true, either one is going to be there. X or not X. Yep, that's always 1. So that's actually kind of neat. So we can actually match that to here. Law of ones and zeros. X and 0 is 0. I have to be X and false. It can never be, the false kind of cancels it in a way. So X and 0 is definitely 0. X or 1 is 1. X or always true. Well, that's true. In fact, I've actually written code where I was testing some test, X, okay? And I wanted to go and make sure you hit this test and go in there. I would literally write in my code, I have my test, X, and then I would say, or 1. And I know if it's or 1, meaning or true, it's going to go into that piece of code. And if I have a piece of code as an X, I never want it to go, I would say and 0. So I actually use these a lot in my coding to have it either always go in the loop, so there, or always get out of the loop. And I'll make a note to say, take this out later when production code is out there. But if I just want to really quick rather than delete the X and write true, I'll actually say and 1, or I'll say and 0 or 1 to either never have to go in the loop or yes, always go in the loop. Kind of cool. This one is from math. Nothing I need to tell you about there. Identity. The identity of multiplication is 1, which is and is true. The identity of or addition is 0. So it's like saying X or false is still X. So the identity of or is false. The identity of and is true. That's kind of neat. So if I have this big and, like the accumulator was adding things together, the identity of addition is 0. So I initialize it to 0. If I'm going to and things together, what do you initialize it with? Right there. You initialize it with true. If you initialize it with 0, I don't care what else you have here, it's 0. Okay? I've got this one. And this one is fun. I'm going to play this song for you. Let me play it. Ready? Here we go. 3, 2, 1.
Idempotent.
Let me play this here for you. This is kind of a fun thing.
Idempotent.
Okay, do you hear that? Do you hear that? Idempotent. Okay? This just basically says X and X. It's not 2 X's. I mean, X times X would be X squared in some other world. But this is X and X is just X. It's got to be X and also X. Well, nothing happened. There was no new information there. X or X, same thing. No new information. Idempotent says this just replace anything of the same with itself. This is the commutative law. I've shared that before. That's a principle now. It isn't necessarily true, but it is true in the Boolean algebra. I mean, it's true in mathematics. It's also true here. I showed you that. We have associativity. We have this. This is the same. Doesn't matter how you parenthesize things. Also doesn't matter how you parenthesize the addition. That's not new and not special. All right, distribution is kind of cool. This means that I can take X and distribute X to both Y and Z, and I can also reverse distribute. If I have a common X, I can pull the X out to have the X in the front. Now, this is the weird, what's the equivalent on the other sid? It's this rule. Look at this rule. This is a really interesting rule, which I can prove for the other terms. Let's actually take a look deep at this rule. Well, I'll start over here, okay? X this. Let's do the FOIL method, right? This is XX plus XY plus That's outside, right? xz plus yz. Okay, let's start using some rules. I don't know. What do you see? You might see the idempotent rule. X times x, that's just x, okay? How about x or xy? Anybody see this rule before? Where's the x or xy? Actually, that's this one. That's the uniting theorem. We can get to that in a second. Here is y and z. I'm trying to get to x plus yz. So this is x or, okay, I'm going to skip. I'm skipping to the uniting theorem, okay? I'm skipping to the uniting theorem. Here we go, uniting theorem, which says xy or x is just x. So meaning it says, okay, it's true when x is true. It's also true if x and y is true, but you knew it was true when x is true already. So this is no new information. The y doesn't help at all. That's just the same as x. So if you add this xy term, it's just x. If I take that, this is x or xy or xz. This, because of the uniting theorem, just becomes x. Therefore, this distribution law, x plus yz, is just x plus yz. So you kind of need the uniting theorem to simplify that side of the distribution, okay? And similarly, this uniting theorem on the right side says, well, let's do it, okay? X or y times x. What is that? Which means x and some other thing that has an x in there. Well, why does that the same as just saying x? Why can't I just drop that off and write a 1 there? Or just cancel it? Why can't I just cancel this term and write a 0? And why can I cancel this term and write a 1? Because x times 1 is x. Why? Well, let's do it. Let's distribute this out. This becomes xx or xy. Actually becomes yx. I do this right. Well, yx is the same as xy. That's this term. That's the commutative law here. Okay, so I got that away. This becomes xy. Xx becomes x. What's that? Idempotent. Idempotent. And x or xy is just x. That's this guy. That's the uniting theorem. Therefore, this kind of is used to prove that guy. So the summary of these is that you probably saw that before. You saw that before. You saw that before. This is new. This is new. You probably didn't know that one. Now you know this one. This is kind of cool. If you ever have an x term or something else that has an x in it as well, cancel it out. If I have an x term times something that has an addition of x terms, I can cancel it out as well. You just get x. That's kind of cool. The last one is really powerful, and you're going to see this a lot in logic. De Morgan's law. This is a kind of neat thing. This says, what this says, you know what this gate is right here? Watch this. This gate is a NAND gate. Do you get this? This says I first take x times y, x and y, this is an and then I put a bubble at the end. That's the bubble at the end. So this is the same as, watch this, an OR gate in which the bubble is on the input. Okay, x and y, and here's the output. Here's how to memorize this. It's pretty cool. You can prove this in logic, but here's a way to memorize this. It's kind of fun. I take my inversion and I distribute it to all 3 terms. So I had this x and y, and I invert everybody. If I invert everybody, this becomes not x. X becomes not x. And becomes OR. And y becomes not y. The same thing on this side. I had x or y, and I invert the whole thing. Again, this is the same as a NOR gate, and it's the same as an AND that has x and y inverted on the inputs. So I can draw it here, the same idea. So this is the AND. This is the same as, here's my this with that. These are the same. Y. I take my not, and I apply it to every term, including the operator. So this becomes not x. This becomes, I invert addition to be multiplication. I invert y to be not y. That's the way to memorize that. It's pretty cool. De Morgan's law. So let's do an example. Here we go. Y is AB or A or C. Is that simplest form? Let's see. Well, look at this. Wow. I can now take this and remove the A. I can distribute, I call it reverse distribution. Reverse distribution there, take that. This A, all right, by the way, this silently was A times 1. Okay, now I have A times B plus A times 1. I can take the A's away. That's both distribution and identity because A is really A times 1. The law of ones says that A times 1 is just, B plus 1. I'm sorry. Let's go back. B plus 1 is just 1. B or 1 is 1. We kind of saw that that was the law of ones. And A times 1 is A. That's kind of, remember that. So there's only a couple you need to memorize from the slide before. If you go back here, the law of zeros and ones is, remember that one? Probably idempotent, you probably need to memorize that one. You know this one, you know this one, you know this one. This one you might need to remember, complementarity. Maybe you didn't know that before. Distribution, you probably know this one. You probably didn't know this one, so you need to know that one. Uniting theorem, also need to know, so know that one, that one. And De Morgan's laws is really cool. So there's some new ones you need to know from this as you go forward. Yielding, this guy, I think of this as like dipping your hands in massage oil and you massage, you're working through. You play some nice music, let's cue the music, and you're hearing, welcome to my massage clinic. I'd like to give you and make you work all the kinks out of your muscles. I see your muscles are very, very, very tight. Let me try to work those out. Hours later, look at you. You walk away as just A plus C. Do you feel better? Thank you. I'm so happy. Please leave a tip in the tip jar. Wonderful. Okay, so that's the idea. If you can use, that's why we use it. Okay, pretty cool. That's it. Next lecture is on canonical forms. We'll see you there.